Hello, everyone. And yet another tooling session. Let's wait for everyone to come in, and then we can start. Yep. All right. I guess let's just start it. Yep. Hello, everyone. My name is John. I'm a DevRel at Mantle. Just a quick intro. Today, I'm very excited to be joined by Paulina from Runtime Verification. They are discussing and building very smart stuff. Securing our smart contracts in the background so that we can sleep calmly. So yeah, I've got very quick intro about the dev tooling sessions. So basically, the dev tooling sessions is a series of workshops that we are live streaming on X and also broadcasted to YouTube to kind of where we invite our tooling partners and let them showcase how to use their tool, why it's cool, and all of those good stuff. So yeah, let me quickly give the stage to Paulina, and yeah.
Thanks, John. Hi, everyone. Shall I start sharing my screen?
Yeah, I guess at least an intro from your side. I know you have a very interesting background, and yeah, please tell it to everyone.
Right. Yeah, fair enough. So hi, everyone. My name is Paulina. I work at Runtime Verification, and today I'm going to present Kontrol, which is our formal verification tool. And so currently, I'm working at Runtime Verification as a technical lead. I'm leading the development of Kontrol that we're going to discuss today. Prior to that, I worked as an engineer at the protocol engineering core unit at MakerDAO, where I also was setting up some open source formal verification tooling. And I also got PhD specializing in formal verification at NTU in Singapore. A few words about Runtime Verification. We're a technology startup providing security services to different industries, including blockchain, where in addition to traditional security reviews and audits, we also focus on developing high-quality open source developer and security tooling for different ecosystems, including, of course, Ethereum, L2 rollups, EVM-compatible chains, and many more, as you will see in this talk as well. And the tools we develop are mostly focused on formal verification. And in this talk, I'll also try to explain why that is important, why it matters in the context of smart contract security.
Yep.
So I would like to, yeah, that's pretty much it for the introduction for me and RV.
Yeah.
So shall we continue with the, okay, good,
For
thanks.
sure, yeah. Obviously, Paulina is a GigaChat in the space with experience from Maker and stuff like that. And also, like, to be honest, runtime verification for me seemed like a very underrated kind of group of people because, like, once I heard that you guys did some verification and auditing for, Eigenlayer and Optimism and, other large DeFi protocols, I was pretty amazed by that. But yeah, let's definitely jump into it. Let me turn on the screen and, yep. Let you
Thank you.
stage. Yep.
Yeah, thanks. Also to praise my colleagues a bit more. I wasn't around, but we did actually verify a lot of large projects and infrastructure, including the deposit ETH 2.0 contract. That was a collaboration with Ethereum Foundation. So we actually did verify and secure, large part of the infrastructure that holds this space together.
Yeah. No one knows why they sleep calmly at night. It's because runtime.
Right. Well, thank you. Thanks for the kind words. So talking about Kontrol, just to put some things into perspective, I would like to start with some brief overview of what formal verification is, what security issues we are focusing on, what Kontrol is, and so on. And so by default, by definition, security is the state of being free from danger. And we know that in blockchain, that is pretty much impossible, but we can try to get as close to that as we can. And if we look at the operation of a DeFi protocol, at how it processes transactions, we'll see that there are actually a lot of components in this technological stack. And unfortunately, a bug can sneak into any of those. Even if Solidity code is secure and correct, it can be exposed by a bug in the compiler, or there can be some issue with the front end, and so on. But luckily, there are some tools that can help us make sure that all of these components are actually secure and can be used safely. And with Kontrol, we are focusing on Solidity code and compiler, because Kontrol actually performs verification, in other words, this security analysis that we do on the smart contract code that is written in Solidity. However, the actual analysis is performed on the EVM bytecode. So Kontrol automatically compiles. It relies on the Solidity compiler for that. It compiles the code into the EVM bytecode, and that is what is actually getting verified. It provides us with some additional security guarantees in contrast to just analyzing the source code itself, because we don't have to make any assumptions about the compiler being correct. So we verify the exact thing that is getting deployed on the bytecode, which makes the results, more, they provide more strong guarantees. So as I mentioned a few times by now, Kontrol is a formal verification tool. So what does it mean? Formal verification is a security assurance technique that lets us mathematically prove that a particular system or the implementation, such as a smart contract or a system of smart contracts, is secure and is correct. However, to be able to generate a mathematical proof of correctness, we also need to be able to define what this correctness actually means. So we need to describe the expected behavior of the system, and then we can prove that the implementation actually does adhere to this description. The challenge in doing that, in writing specification, that is the formal verification term for this, is that it's actually pretty challenging to write this very, very extensive specification that covers all possible, all aspects of the smart contract or some other implementation behavior. So the one thing that we can do is to define so-called set of properties. A property is also a statement about the implementation, about what the smart contract in our case should or should not do, but they focus on some specific aspects of the code behavior. One very common example of a property is the so-called balance invariant in ERC20 tokens, which basically states that the sum of user balances should also be equal to the total supply, which implies that no tokens were lost, no tokens were generated incorrectly, and so on. Different tools provide different languages for writing these properties. Some tools provide custom languages. We rely on Solidity code, so we let the user provide these properties in the form of foundry tests written in Solidity, just to make it easier for developers to write the specification, especially for people with no formal verification background. So we just try to make it as easy as possible to use Kontrol as a formal verification tool. So in addition to specifying these properties, what we need to make sure that the code is implemented correctly is also the code itself. So another input that Kontrol takes is the smart contract source code. As I mentioned, Kontrol works with Solidity smart contracts. So it compiles and translates it to the formal representation that we can reason about automatically. So it is a transparent process. You can see what actually is happening, but it happens automatically, so no additional actions are needed. The translation to the formal representation is needed so we can run some mathematical proofs on this generated model of the source code. So after that step is done, the tool analyzes the code that it is given. It checks if this code indeed conforms to the properties, to the specification that was given to the tool as well. And if it looks correct, then it tells us that the proof passed, and we have mathematically proved that the smart contract behaves as intended. If something else happens, if one of the properties is getting violated, then Kontrol just tells us that something failed, and there is some particular aspect of the code behavior that does not really adhere to the specification, and it also would show us how exactly, under what circumstances, under what inputs, this failure occurs. So I'll also show an example of that later in the presentation. I have borrowed this diagram from this blog post that you can see the link to on the slide. That is a joint blog post by us and Audit Wizard, so you can also check it out if you're looking for some intro to formal verification materials.
Very quickly, just to chime in.
Yep.
So just to clarify that Kontrol is what we're talking about today. The last step, the formal verification tool step, this is what you guys have been building. And then could you tell us a little bit more about like the formal model, right? how does the formal model look like from a smart contract source code, right? And is it part of like the tool suite to generate that formal model, or do developers have to go out and do them by yourself and then plug it into Control?
All right, thanks for this question. So the only thing you need to provide a control is the code for the smart contract you're analyzing and the Foundry tests that you're using as specification. Everything else is handled by Control automatically. So formal model is generated automatically. Basically, the generation consists of two steps. The first one is running a compiler, so getting EVM bytecode for the code. We're running Forge build under the hood, so we are using Foundry's capabilities for doing so. And the other is using that to generate some key files. So key is the formal language that we use at Runtime Verification. We also develop and maintain it. That is the formal foundation of all our formal verification tooling that also allows us to develop tools for different ecosystems while having the same formal verification like reasoning foundation. So yeah, basically we just take this bytecode and we put it into proper places in this key file, written in the key language that we have. It all happens automatically, and that is what is actually getting executed and verified. That being said, one important thing that I also would like to mention here is that when it comes to executing this key representation, we are relying on KVM. That is also a tool. It is EVM semantics implemented in K. It is also developed and maintained by Runtime Verification. So it is essentially a client for EVM, but written in K. So it allows us to do the reasoning, but it is also a full client. Really, it can it passes Ethereum's conformance test suite for clients. So we actually have a proof of it working correctly against the test suite for clients.
Yeah. So KVM.
So I hope that clarifies. Yeah, KVM.
Yeah.
I don't have a link to it in the slide. I can send it a bit later, but generally it's in GitHub under Runtime Verification, EVM-semantics.
All right.
So it is also open source. All of that is open source.
Oh, that's super cool. And I love that you guys are working tightly with like the Foundry, like existing tools. So there's very low kind of learning curve for people to just start using Control. Yeah.
Well, hopefully that's what we are working on. But I have some examples of that in this talk. So I hope to convince you guys. Yep, thanks. So if I can continue, that is also a very brief overview before we look into some more details about what Control is. So just to summarize, it is a formal verification tool. It relies on specs written as Foundry property tests. We have an example on this image that you can see on the slide. So there is a test written for Foundry. It is part of the Foundry default template. So it calls the set number function of counter. Counter has the variable called number that is being set to this parameter x. And then there is a assert checking that the number has been set correctly to x. Control can prove this. Foundry can prove this as well. It is not a complicated test, but that's what it looks like in essence. Control verifies EVM bytecode, as I've mentioned. It is fully open source. So also one important thing that I wanted to mention is that it's open source, it's free to use. You can set it up for your project. If you already have Foundry tests, you can just give it a try and see if Control works on the existing tests that you already have, because then you just get better security guarantees on the tests that you already have developed. And of course, we welcome all contributions. We have just released 1.5 weeks ago or so, we have just released version 1.0, which is very exciting because we have put a lot of performance, UX, a lot of improvement really. And if by any chance you tried Control before, please give it a try again. It got much better than what it was even a few months ago. And also on the slide, I have a link to the Control implementation in the GitHub. In our repository, you can also find some instructions on how to build it. You can also look at how we develop it. And as I've mentioned, any PRs are welcome, issues as well. So I think that's the last intro slide that I have here. So also just to put Control on a scale of security assurance tools and formal verification in general. So on the slide, we have ranged them according to the level of confidence that these security assurance techniques provide us with in terms of security of the implementation we're analyzing. And I understand that manual review being the least providing the least level of confidence is debatable, but what I want to say is that it very much depends on the particular person performing this review. And in contrast to that, automated tools are a bit more consistent. So static analysis, for example, that's also a very, very common security assurance technique. It's highly usable. Slither is one example of it. So what it does, it automatically analyzes the source code, or it's usually high level source code or intermediate representation, and it tries to detect some common vulnerabilities according to some patterns. So it essentially does pattern matching on the source code. So it can identify some issues like reentrancy, overflow, and so on. It's very lightweight, so I personally don't see any reasons not to use it. The problem is that it doesn't really provide you a lot of information about this business logic or other types of behaviors other than just detecting these common vulnerabilities. So in that sense, unit testing, fuzzy informal verification provide better coverage, and I'll explain why using this example that we have here. So I have prepared this for today's talk for illustration purposes, but let's assume that you have a project that performs some fixed point arithmetic operations, and it uses this library in order to do so. There are a lot of libraries doing that, really. That is just one of them. And let's assume that this library has just released a new version, and there are some diffs, and among them there is this one. So even if you look through the diffs in the dependencies, which I strongly recommend everyone to do, from my experience, you can still miss this particular change. So what happens here? This function essentially is a scaled multiplication. So it multiplies x and y, and normally it reverts if there is overflow between x and y when doing this multiplication. However, after this modification, it would also revert if x is equal to this pretty specific concrete value. I tried to disguise it a bit as a bit mask, so it's a bit less suspicious than it could be if it was another concrete decimal number. But I haven't tried to hide it very, very well. So essentially, what we've done here, we have introduced this invalid behavior because now this function is going to revert when it really isn't supposed to revert. And we'll try to see how well these different techniques would actually be able to find it. Generally, this function, the original function, is taken from the Solidity library. It's very popular. It provides gas-optimized implementation of a lot of common types of contracts, really. It is safe to use originally without this modification. We have proved it previously with Kontrol. There is also a link to the repository where we have done that a bit later in the talk. So the problem with implementation, such as this one, is that it contains this assembly, right? It's a gas-optimized implementation. That is why there is this inline assembly. It makes it difficult to use static analysis tools on it because typically they do not really work with assembly. Another issue is that it is a non-standard problem. So it doesn't fall into these categories of common vulnerabilities. There is no overflow, there is no reentrancy, which makes it hard to detect it using these pattern matching techniques. And it being written in assembly also means that there are no compiler checks. Compiler actually does insert quite a lot of checks in order to avoid some common issues. For example, starting from Solidity 0.8, there are overflow checks getting inserted automatically. Also, the small what function is not payable, which means that if we try to transfer ether to it, it's going to fail, which is also powered by this compiler inserted check. If we write it in inline assembly, then it really isn't going to happen. All that means that we have a higher chance of detecting this issue doing a manual review, but assembly is also less readable than high-level Solidity code, which also introduces additional challenges. So what can we do? We can write some unit tests. I have some examples of unit tests here on the right in the slide. So the first one, for example, just calls this small what function with two values, x being 5 and y being 0.5. And then we check that the result of calling this function with this value is 2.5, which is correct. And that is essentially what unit tests do. They examine some particular behavior on some particular concrete inputs, such as 5 and 0.5. Unit testing is also an extremely powerful technique that definitely should be part of any development process. The only problem with that is that it actually provides us with limited coverage. So we still don't have complete information about how this small what function behaves. We only know that it works for these two concrete values. We can try to increase coverage by just adding more values, examining more function calls with different concrete inputs, but it will take us a very long time to enumerate all values corresponding to this UN 256 input parameters. Another way to increase coverage that is recommended and is generally the right thing to do is to add tests that examine all possible branches. So if you have an if statement, then you would like to write a test that examines a true branch and then also another that examines the false branch. Also, another problem with that is branches may not really be obvious because of these compiler inserted checks. So an alternative to do this, not an alternative, a complementary technique to use to increase coverage is fuzzing. But yeah, so to summarize unit tests, it only examines one execution path, which does not provide us with a lot of information. So fuzzing, I think is very well described by this tweet saying that a QA engineer walks into a bar and then orders a beer, 0 beers, max 256, max 256 beers, -1 beers, and so on. That is what fuzzing does automatically. So fuzzing just calls this function over and over again using different concrete values in an attempt to identify some edge cases corresponding to some of these values. So here we also have a test that is a fuzzing test, also it's parametric. So it takes inputs different from unit tests. It takes variable x and y. And what we do in this test is we check that if there is no overflow, then the result of calling malwad would be the same as calling as computing the same thing in Solidity, which we can actually examine with our eyes. So we assert that the result is the same, meaning that it is equivalent to the Solidity implementation. Alternatively, it should revert. So we use this expect revert cheat code in Foundry, which we also support in Kontrol, to make sure that malwad would revert if there is overflow. Generally, Foundry is, and fuzzing in general, is also a pretty powerful technique which can examine a lot of execution path and identify a lot of issues. In this particular case, however, it cannot really identify this value x being equal to this concrete to this constant, that would make this test fail because of this unexpected revert. So we can see that the test passed with this default number of runs, which I think is 256. And so that brings us to the summary of fuzzing as a technique. It is very useful. It explores a lot of paths, but not all of them. So it's not guaranteed that you will actually look into all possible behaviors, which means that you cannot really prove the absence of bugs. You can just prove the presence of bugs if you identify them. And that what brings us to Kontrol. So on this slide, I have a test that actually, that is a Kontrol test, but it looks exactly the same as Foundry test. And if there is one takeaway from this talk today that I would like you to, to take with yourself, it is that Kontrol works with Foundry property-based tests. If you have any Foundry tests in your code base, you can just give Kontrol a try and see if that works. Kontrol can also let you do more powerful things, but I will explain that in a bit. When we use Kontrol on the same test, it would actually tell us that the proof has failed. That's what this message suggests. So proof failed, and the proof failed if x is equal to this decimal constant, which actually corresponds to this hexadecimal constant as well. So Kontrol can actually identify this failure. And that is because Kontrol explores all possible executions. So it analyzes it tries to mathematically prove that this behavior holds for all values of x and all values of y, while Foundry or other concrete execution tooling would just try to invoke the same function over and over again with concrete x and y, which would be incomplete. So Kontrol generates a mathematical proof that the behavior holds for all possible inputs, which means that it covers all behaviors, which also brings us to identifying this issue that we have identified. So now I would like to move on to a more practical part of this workshop. So I have prepared some materials on how to rerun the things that I'm going to show. So this slide has the instructions on how to install Kontrol. Either you can build it from source, or you can install it with KUB, which is our tool that we have developed for installing runtime verification developed tooling. You can also install Kontrol with it. You'll just need to run 2 commands, one installing the KUB itself, the other installing Kontrol. We also have some documentation regarding the installation process. So you can see these key app cheat sheet here in our docs. And generally, the slides also have a link to the control documentation. You can find some installation instructions. You can find some control examples. Basically, just basic information about how to run control. We also have some examples of issues that fuzzing tools such as Foundry cannot find that control can, which is not the same thing that I have just showed you. And in addition to that, I have also prepared the repository with also some instructions on how to rerun proofs in the README file and the Docker image. So if you don't want to install control right now on your machine, but you would like to give it a try, you can just pull this Docker container with control pre-installed and all the proofs pre-run. So you can just run commands that I'm going to show you today and see, see what control outputs for these proofs. So now let's actually take a look at proving something and how it looks like with control. So the first step that actually performs this compilation and translation to formal representation in K is running control build. So as I mentioned, I built this project beforehand, and I also pre-ran the proofs because each takes a minute or so in this project, just so we won't have to sit around and wait for it to finish. But it will take a minute or so if you run it yourself. So the first command to run is control build, after which you can actually run some proofs using the command called control proof. Here, I have a test that is the same thing that I have just shown you on the slide. So it is a Molbot test. It inherits the test contract from Forge STD. So it is a normal Foundry test, really. It can be executed with Foundry as well. And here I have the modified Molbot function that we have just seen in the slide. This one is supposed to fail. And I also have added the actual Molbot function that we are going to prove right now, just so you know that we can also prove that things are correct and not just identify some issues in them. So that is the Molbot function taken from Solidity. And here, once again, we have the test that proves that if there is no overflow, then it behaves exactly as the Solidity implementation would. Otherwise, it would revert. So the command we'll run is control prove. And in order to select the test to be analyzed, we can provide the name of the function of the test, or a prefix if we want to analyze several tests sharing the same prefix using the --mt or --match-test command. Here we're mimicking Foundry's interface, and that's what we generally try to do. We try to make our interface as close to Foundry as possible, and semantics of the analysis as well. So because I ran it previously, the results load pretty fast. Otherwise, it would take this 2 minutes to run this proof. But what we can see is that the proof has passed. So now we have this mathematical guarantees that indeed Molbot function behaves correctly. One more function that we have proved for Solidity is log2. You can also see it in this repository where we have control Solidity proofs that I have in the slides and will show a bit later. So that is one type of proofs that we can run. That was an equivalence proof. Really, we were checking that one implementation, the gas optimized implementation that is hard to read, is similar to the Solidity implementation that is easier to read, really. But we can actually use it to analyze more things. And one other thing that I have that we have in this project is some proofs that are inspired by some of the Optimism code. And the reason for this is that we have completed an engagement with Optimism where we have helped them to verify that pausability mechanism works correctly. So what we were checking is that if some contracts, such as Optimism Portal, have been paused, then the functions cannot really be called. They are going to revert because that's how we expect it to work. So for today's workshop, I have prepared a slightly simpler version of that, just to make it easier for everyone. So we'll look at how that can be run as well. But in some later slides, I also have links to the actual engagement, and we have published several blog posts about it. So please feel free to look at that as well, because I guess that is pretty relevant for you guys. So what we have here is this portal contract that is heavily inspired by the Optimism Portal contract, although it's slightly simpler. It has a guardian that corresponds to the deployer. of the contract, so it's message sender in the constructor. I have also slightly simplified the possibility mechanism, so it is implemented in the same contract. It sets the variable post to true if it is called by a guardian. Another function that belongs in the original Optimism portal contract is donate is, which just accepts Ether value. So everyone, I believe, is should be able to call that. That's the simple test that we would be able to run for this. And here is the function with the same really signature that we have analyzed in the actual engagement. I have omitted implementation, so I don't have to explain what happens, frankly speaking. But that is one of the functions that should revert at all times, whoever calls it, if it has been paused. So that's also one of the things that we'll try to check. So the test, once again, would look like a normal Foundry test. We have this test as a parent that is forge std test. There is a setup function. Setup function is also respected by control. So it's going to be run first, and then all tests would run on top of the result of executing setup function, very similar to how it is done in Foundry. And here is some more or less realistic tests that we can run for this. We can check that a non-guardian cannot pause a contract. So this functionality should have some access control checks on it. And what we want to make sure is that no one can call it other than this authority in an account that is authorized to do this. So what we can do is we can make sender a parameter. So we provide this address sender as a parameter in the test, which means that we are going to assume that sender could be anyone. It can be any address. We'll try to generate a proof that this behavior holds for all possible values of sender. We refer to these variables such as symbolic variables. So symbolic essentially means that we are checking for all possible values. However, if we want the function to revert, it should not be a guardian. So that is where we can use Foundry cheat code, vm.assume, which we support. And generally, we support a lot of Foundry cheat codes. We have some additional ones that I'll cover a bit later. So what we are saying here is that sender could be anyone. Sender could not be guardian. Then we can use vm.prank cheat code to make it look like pause is getting called by this sender. And we also provide the expect revert cheat code because we're actually expecting this to revert. So generally, now if we run control proof match test and we provide the name of this function, we will see that it passed as well because this function actually is implemented correctly, although it's also pretty simple. I have a couple more tests. So I guess what I'm going to do now is I'll run control proof with some parallelization. So if we run control proof, it's going to pick up all tests that that satisfy particular criteria, which we have. So control considers tests to be functions starting with test, proof, or check. And it is also should be part of the test contract or should have, the contract should have the isTest Boolean variable set to be true. So essentially, if it's a Foundry-based project, it will pick up everything that starts with test in the same way as Foundry does. So this J7 ensures that all these functions are actually being executed in parallel. And you can see that these 7 workers are being used to run these tests. One more thing I would like to mention while we wait for this to finish is that control build and control proof can be parameterized by the options. You can see them by running, for example, control proof help. And here, for example, you will see something like match tests, which we have used previously. In addition to that, we can also parameterize it with control.toml. We have added it fairly recently. We believe that it's easier because you don't have to memorize all these options that you have passed in some previous commands. So it just makes it easier to reuse. Basically, it is somewhat similar to foundry.toml. We have build, proof, and so on options for fields for different commands. So you can also use it to parameterize the execution. And so what we have here, one other test that we can write just to try to debug something, we can try to define a test that makes sure that donate is can be called by anyone. That is not something we have verified for Optimism. I'm not entirely certain that it is needed, but that's a way to showcase control. And it is a valid property, perhaps for at least one project. So what we can do here, once again, we say that center is symbolic. It is a parameter, and we also make tokens symbolic. So tokens is the number of Ether that is going to be sent to donate ETH by the sender. What we can do, we can also add some assumptions about sender being a so-called fresh address. So we can add an assumption saying that it's not a test contract. That is not strictly necessary, but it is something that we do to make sure that it's really the address that is not one of the known addresses. It is not the VM that is the cheat code address in Foundry, as you can see in the help message. And it's also not Portal contract, because Portal contract would not really be able to call its own donate is function. Then we have this trunk, then we call donate is. So if we look at what happened, we will see in the output that the test has failed. And if we inspect what actually happened, if we look at this model, so that is what we call a counterexample. That is a control showing us what exactly, under what circumstances there is a failure that occurs during the execution. I guess that is, that is the one. We will see that the path condition, that is basically the condition that should be true in order for us to get to the state where the failure occurs, tells us that the failure happens if tokens is greater than 0. So the model, the counterexample, also suggests that tokens is equal to 1. The way to interpret this really is that sender doesn't really have any tokens. So if the value of if the number of Ether tokens that we attempt to transfer is positive, then it's going to fail. What we do in this case, if we want to make sure that we analyze the case where we actually explore tokens actually getting transferred, what we can do is we can add the vm.deal cheat code, which is also one other Foundry cheat code that we support. So here we'll have some symbolic balance, and we'll try to deal the symbolic balance to the center, so we can also see if the user can transfer some tokens and whether that would work. One thing I wanted to show here as well is the use of control cheat codes. So this kvm.freshAddress is the control cheat code. The use is pretty similar to Foundry, where we say vm.assume, for example, or vm.deal. To use control cheat codes, they can be accessed by this kvm.freshAddress. And where we actually get it from is the control cheats contract, which can be installed as part of the control cheats library. So the way to install it is to say forge install runtime verification -control cheat codes, and that is going to place this contract under your lib folder in your Foundry project. So here you can see some of the cheat codes generating fresh symbolic values. So this, for example, will generate a fresh uint56 variable that is going to be symbolic. It will behave similarly to it being a parameter in the function signature. And there are also some more cheat codes that can be used, such as, for example, so there is this fresh address, fresh bool. Symbolic storage is the cheat code that we use quite often. I think we'll use it in this in the example here as well. Symbolic storage basically means it accepts an address, and what it means is that whenever we read something from the storage of this address, the result is going to be symbolic. So we'll assume anything can appear in the storage of this address. So getting back to our portal contract, basically in the same way we can make sure that sender is symbolic, we can once again assume that it is not a portal contract that would not be able to call itself. And if we add vm.assume statement suggesting that balance that we are dealing to the user is greater or equals than tokens, which essentially means that the user has enough tokens to transfer, then we'll see that it actually passes in a bit over 1.5 minutes, which is pretty fast. So that is how the process of writing tests using cheat codes in both Kontrol and Foundry looks like, as well as the process of debugging that. And now one final section of the proofs that I would like to show is actually something more optimism related. So as I mentioned, what we were proving is that pausability functionality works correctly. So what we want to check is that if the contract has been paused, we are expecting a revert when a particular function, such as proof withdrawal transaction, is called. As you can see here in the results, it actually passes. But an interesting thing here is that if you look at the signature of this function, you will see that there are a lot of dynamically sized types. So there is an array of bytes, and this withdrawal transaction also has bytes data component element there. And that is what is very challenging for formal verification tools because of the way ABI encoding works, because of the way that if we have a symbolic array, then potentially it can have any number of elements, and these elements are encoded in according to this ABI encoding standards. So it has this lengths, offsets getting stored. So honestly, it's pretty challenging. We have a way to deal with that and even perform unbounded verification where we don't have to limit the lengths. But also one thing that we have implemented to just make it easier is this not spec comments. They're control specific. What they let us do is they let us specify the lengths of all these arrays and byte arrays. The reason why we need this is that we cannot really, we cannot really use vm.assume to make some assumptions about their sizes, because these checks are inserted by the compiler. So compiler inserts a lot of checks on the well-formedness of this symbolic call data. It will check if the array has enough elements, if it is long enough to hold what it should hold, and so on and so forth. So if we add some vm.assume statements in the body of the function, we'll start reverting and branching on this well-formedness checks before we actually get to execute this body of the function. The solution we have decided to go with is to just add this not spec comments that let us say that withdrawal proof has 2 elements, each is 32 bytes long, and it can have any other value really, and that data in withdrawal transaction is also 32 bytes long. So what we can prove is that if we post the contract, we expect the function to revert, and it actually does revert. We can also make it a bit more general, and that is what formal verification tools such as Kontrol let us do. In order to explicitly say that the contract has been paused, as we would have to do in Foundry, for example, we can instead assume that the storage is symbolic. So as I mentioned before, what it means is that the portal contract storage is symbolic, or whatever we read from its storage is also symbolic. So this post function corresponds to the post Boolean variable. And what we say here is that if it has been set to true, then we are expecting the function to revert. If it has not been set to true, we are not expecting it to revert. And the execution here, the execution would branch into 2 different execution paths. One where we expect it to revert and post is true, and the other where that doesn't happen. And then we just call this proof withdrawal transaction. And once again, we'll see that this test does pass in less than 4 minutes. The way for us to explore what actually happened, one useful command in Kontrol that we can use is control list. It prints the basically all proofs that have been generated in this project. And that also provides us with a way to inspect the control flow graph. So what we can do, we can run a command called control show. Then we need to provide the name of the function or a signature, such as this one. And that will show us this, what we call KCFG, or control, or K control flow graph. And it's just going to print us what actually happens during the execution. So we can see all these nodes correspond to generally a block of statements that were executed. And here we are branching on a constraint saying that something that we have read, a Boolean we have read from symbolic storage at slot 0 is equals to 0. What it really means is that the post variable equals 0 or it is false, and then the execution just continues. The call is successful, and we are also finishing the proof with this EVMC success status, meaning that nothing has failed really. An alternative branch that we are taking is saying pretty much the same thing, but it has this notable here, which means that whatever we read, the Boolean we read from storage slot 0 is not equal to 0, it is 1, which means it's true, which means it was paused. Then we can see that here we have been executing a call that ended with EVMC revert status, meaning that the function has reverted, but we have expected this revert. So the execution still finishes with EVMC success status. And that is how we analyze 2 different branches of the execution, while also running this more general test than having to pause contract manually and so on. So That is, I guess, pretty much it for what I had for the practical part. If anyone has any questions, please let me know.
I do have a question.
Sure.
So you mentioned that this is the control is kind of integrated into Foundry, right? So then the entry point for any developer to start building their dApps, like having formal verification in mind for future, would be the control repo, or is this something I can download through the CLI, or is it KUp that you mentioned?
It is KUp. So you can download it using the documentation. The simplest way is to run KUp. So you can run KUp install control, and that would do it. It might take some time on the first run, just because it installs a lot of things that are powering control under the hood. I think it would also install the new version for me right now, because we have just published one. But yeah, that's the easiest way to do this. Yeah. And if you have a Foundry project, then you can just install control and run control on the project that you already have, such as this one, for example. Alternatively, if you would prefer to install it manually, to build it yourself, that is the control repository. We also have some instructions here on how to install it. So there is a fast installation with KUp, or there is building from source process that you can use if you would just prefer building things yourself, or if you would like to contribute, because it also allows you to test it locally.
Awesome.
And then once you have it installed, as I mentioned, you can just run it on top of the project that you have and see if that helps. If you would like to use some control cheat codes to run more symbolic tests, then you can also do forge install control cheat codes and just continue add this control cheats dependency to the test contract that you have.
Yeah, that is amazing. That was such a masterclass from Polina, by the way. I'm not sure if you were breathing or not, but that was a lot of
sorry about that.
a lot of content in one kind of go. And maybe to very quickly kind of wrapping it up, I would like to ask, like, in terms of speaking to developers, right? What would be like the one-liner pitch for them to start thinking about formal verification? Because I speak a lot to developers, and for them, the options at the first glance is like manual review / audits, or unit tests, obviously, or it's static analysis or fuzz testing. And I don't see like formal verification getting mentioned very often. But yeah, what would be like the pitch one-liner for those kind of developers to start using formal verification? Because yeah, these days, there's a lot of hacks. There's a lot of very nasty things going on in the space. So yeah, what would you say would be kind of the best?
Yeah. Right. I'm not sure I can produce a one-line pitch, because that's not how I operate, as you have observed in the last 45 minutes. I would say that I know that formal verification is traditionally associated with a lot of effort needed to set it up, but it is not exactly true with control, at least anymore. So formal verification provides the guarantees that are hard to get elsewhere. No manual review or fuzzing or unit testing can really prove the absence of bugs. You can find some, but you can never be certain that you haven't missed something. And mathematical proofs that are performed by formal verification can actually provide you with this guarantee. So I guess you can sleep better. One more thing that I can say, that is what I actually meant to say here on this slide, is that it can scale to actual code. I know that I have been showing some examples, but we are running this on our client's code bases, on pretty big code bases. We have some features that make it work better. You can see the control proofs that have been integrated in Optimism monorepo. And the point I want to make here is that we are running this test on CI, and the performance of control has really improved tremendously. And you can see we have run some evaluations locally, so it got 4x times faster on some of the tests that run on Optimism CI. And what we are trying to go with this is towards a more sustainable security model for projects. And basically just, so the hashtag that we are using is control your code, which means that we are trying to make developers take control of their code themselves, over having to rely on this constant stream of manual audits that are pretty that are pretty expensive. So what we can get with Kontrol, and especially having Kontrol run on CI, which is mentioned here, we have this GitHub action that you can install using through this QR code, or you can just follow this link. It is free to use, so you can install it in your project and just have it running. We offer some services such as CAS, which is K, or Control as a Service. So you can offload the compute to us. But basically, you can just set up control tests once using the Foundry proofs that you already have, and then have it run on every commit, which means that you will be sure that this formal verification proofs that are very comprehensive are still passing on new updates. So that can either substitute or at least complement the having to rely on this manual reviews of new updates, because we know that they actually break stuff, leading to a more sustainable security model for companies, and also providing better security guarantees, to be fair.
Yeah.
So I hope that did sort of answer.
That's a great answer. Yeah, I think the major barrier for kind of doing like, I guess less developer heavy teams using formal verification was that it is quite a challenge to boot up some like a proper test with like a formal verification. But I think these days with like tooling providers like Runtime Verification, you guys have Kontrol. You also have Symbolic. Hopefully, we'll talk soon about that. So yeah, great. Any last notes for us, Paulina?
Yeah, I guess that's about it. Thanks for mentioning Symbolic. We do have this debugger that is called Symbolic. It's in beta. It also has some online version that you can find using this link. There are some. We published several blog posts about how we verified optimism proofs, because we had implemented some features to make sure that control works well on large code bases such as this one. So please feel free to check those out too. And yeah, thanks for having me. I guess, yeah, I agree with what you have said about there being a high barrier for people, especially developers who don't really have enough background or time, honestly, to set up formal verification tools. But we really have focused a lot on controls UX and performance, and it really has gotten much better. And it does work out of the box with a solid number of Foundry tests. So yeah, I guess I would just recommend to give it a try and see if it works well. Please let us know if you're running into any issues. Here are some of our socials. We have Discord, we have Telegram channel, we have GitHub where you can submit issues, we have Twitter. So please feel free to reach out to us using any of those channels. We would be happy to help.
For sure. Yeah, go follow RV, Runtime Verification, also Paulina. I think this is one of the, also, yeah, Gregory as well, the person who connected us. He's yeah, probably if you're somewhere in the world going to conferences, you've met Gregory at some point. And to be honest, I personally think Runtime Verification is one of the most underrated teams out there. I hopefully there's going to be a lot of buzz around your name very, very soon. But yeah, thank you, everyone. Thank you, Paulina, for joining. My last kind of a few words here. Please do join the Mantle community if you're a developer. If you're a developer, please feel free to use this link to join the developer channel. All right. Thank you, everyone. See you next time.
Thank you so much.